We present a practical approach to real-time simulation of fracture with oriented particles. Our method requires not only the geometry of a deformable body, but also its fragment meshes. The fragment meshes can be obtained in many ways. We employ the simple approach of applying k-means clustering to the centers of tetrahedra, while considering the connectivities in the mesh. Each cluster of tetrahedra becomes a fragment corresponding to an oriented particle. The covariance of the tetrahedra gives the initial orientation of the particle, and the oriented bounding box gives the radii of the particle, as in Miller's work. For visualization, we used only 20 particles in this example. Nevertheless, the simulation result is interesting. The result obtained with 100 particles. Fragment meshes can also be obtained with Voronoi shattering. The next experiment compares plastic deformation of 3 vertical elastic bars with different plasticity. The top end of each bar is twisted for one full rotation, while its bottom end is fixed. The bars undergo large amount of plastic flow during the twisting, so they do not return to their original shapes after being released. The left torus is purely brittle and the right one is ductile. Each torus consists of 200 particles. The bodies are struck by a heavy weight. They undergo large deformation and fracture due to collisions with the weight and the floor and self-collisions. Each body model consists of 300 particles. In this example, 4 plates with the same simulation mesh, but with different material parameters, are struck by a heavy weight. The same simulation was shot with a different camera angle. The top left plates exhibit the behavior of nearly brittle material. The material becomes more ductile in clockwise order. The proposed technique was implemented as an Autodesk Maya plugin for content creation and offline rendering. The deformable model can be exported into the Unity 3D plugin for interactive application and real-time rendering of large scenes. We developed a very simple first-person shooting game with the Unity 3D game engine. The simulation is performed with a simple parallelization using OpenMP and GPU skinning. Currently, collision detection and response are handled in a single core. Nevertheless, the simulation runs about 30 frames per second in this example. The final experiment is for a stress test. We just drop off deformable models without any user intervention. The simulation runs about 30 frames per second in this example.